Good morning. Can you hear me?
Yes, sir.
Okay. So welcome back. I guess the paper was okay. Now, last time we had been talking about linear dependence, oblique independence of vectors. And we had seen a method by which actually we can check whether a given set of vectors is dependent or independent using that Gramian matrix method. Do you remember?
Yes, sir.
So today we are going to talk about linear dependence, oblique independence of vector functions. I guess you remember what topic actually we are studying. We are basically talking about we are basically trying to discussing the controllability tests. और कंट्रोलेबिलिटी टेस्ट वो जो थ्योरम मैंने उसमें स्टेट की थी उसमें एक टर्म आई थी ग्रामियन की, तो हम उसी को थोड़ा सा अंडरस्टैंड करने की कोशिश कर रहे हैं. तो लास्ट टाइम हमने देखा कि अगर आपके पास n vectors हो each having m components, so in that for that you have to check whether this given set of vectors is dependent or independent. So you actually can do that using a matrix known as Gramian matrix, which is a square matrix, and checking its rank. And we found that if the Gramian matrix, the rank of Gramian matrix is, if your Gramian matrix is a full rank matrix, in that case, the given set of vectors is independent. And in case it is having some rank deficiency, we say that the given set of vectors is dependent. Now we are going to extend this theory to check the dependence and independence of vector functions. What do you mean by vector functions? Vector functions are basically vectors whose components or whose elements are functions of time. That's what are vector functions. Functions or vectors whose elements are functions of time. Okay. So let's say you have some function like this. You have got a vector function like this. You have got some function, let's say ft, and its elements are, let's say, e to the power minus t sine t 1 plus e to the power t e to the power t. We call this as a vector function. It's a row vector function. Similarly, you can have column vector functions. So we have got a given set of functions and we have to see whether this set of vectors is dependent or independent. So how do we do that? How do we check the dependence and independence of a set of vectors, set of vector functions? That's what we have to discuss today, because this is what directly we'll be using in that controllability test. This will be directly useful in defining the controllability Gramian that I discussed with you that I just stated last time. So now let's say on the same lines on which we have tested, we have checked the dependence and independence of vectors, we'll develop the theory on the same lines for vector functions. So we'll consider a set of n vector functions, each vector function having m components. Consider a set of n row vector functions, each having m components. And we have to The problem is that we have to test these vector functions for linear independence of the independence. Okay. So in order to do that, so we have got a set of n vector functions. So we define a vector function matrix as capital F is equal to, it's actually a matrix whose rows are these vector functions. So I have got f1t, I've got n vector functions, f2t, so on, up to fnt. And each vector function is having m components. It's like this actually. f1 1t, f2 1t, so on, fm 1t. Second is f2 1t. This is the second vector function. Sorry, this is actually f1 2t. This is actually f1 mt. So this is f2 1t. Then you have got f2 2t, so on, up to f2 mt. इसी तरह आपके पास n vector functions है. So this is n1t, n2t, so on up to fnmt. तो ये जो n vector functions हैं जो कि rows हैं इसके, मुझे इनकी dependence independence check करनी है. So how do you check the set of vectors for dependence and independence? The same logic will be applying here. So the given set of vectors will be linearly dependent if there exists a non-zero solution to this equation. Which equation? To the equation stated as alpha 1 f1t plus alpha 2 f2t plus so on alpha n fnt is equal to 0. If there exists a non-zero solution alpha to this equation, then we say that the given set of vectors is linearly dependent. If the only solution to this equation is all alphas equal to 0, then we can say that this given set of vector functions is linearly independent. So the same methodology that we used last time for developed last time for evaluating a given set of vectors for dependence and independence, the same methodology we'll be using here also. So what I will do is, just see, I'll call this as equation A or equation 1, this Roman 1. I post multiply equation this Roman 1 by F1 transpose. So what do we get? I get alpha 1 F1t F1 transpose t. So this is also a function of t plus alpha 2 F2t, then F1 transpose t plus so on alpha n fnt F1 transpose T equal to 0. Is that okay? What is the size of F1? Yes, tell me. What's the size of this F1?
1 cross M, sir.
What? The size
1
of
cross
F1?
M.
1 cross M. And what is the size of F1 transpose T? M cross,
M cross 1.
So this is a scalar actually, isn't it? The product will come out to be 1 cross 1. Is that okay? So this is a scalar
Yes,
0
sir.
here. This is a scalar 0 here. Now after that, what I do to this is I integrate it on both sides over the interval T0 to T1 over some time interval. So I integrate this equation integrate equation 1 over some time interval T0 to T1. What do I get? I get alpha 1 integral of T0 to T1 F1T F1 transpose T dt plus alpha 2 integral of T0 to T1 F2T F1 transpose T dt plus 1 alpha n integral of T0 to T1 Fnt F1 transpose T dt equal to 0. Is that okay? So once I do that, when you will evaluate this integral over a definite time interval, T0 to T1, where T0 and T1 are known, they'll come out to be constants. They'll come out to be some values. So this equation, I call this equation as equation number 1. Okay. Same way, I multiply this equation, go on multiplying this equation. Next time, multiply it by F2 transpose T and integrate it from T0 to T1. So multiply equation 1, this Roman 1, by F2 transpose T. I'll put it in single step now and integrate over the time interval I integrate it over the time interval T0 to T. So what do we get? I get something like this. This is alpha 1 integral of T0 to T1. Here I have F1T, then F2 transpose T dt plus alpha 2 integral of T0 to T1 F2T F2 transpose T dt plus 1 alpha n integral of T0 to T1 Fnt F2 transpose T dt equal to 0. This I call as equation number 2. Are you following me?
Yes, sir.
I go on multiplying it by F3T, F3 transpose T, F4 till I reach Fn transpose T. So go on multiplying. So you just go on multiplying like this. I'll show the last one. So you multiply equation 1 or post multiply equation 1 by Fn transpose T last में आ जाएगा and integrate over the time interval t naught to t1. So what do we get? We get alpha 1 integral of t naught to t1. Then we have f1t fn transpose t dt plus alpha 2 integral of t naught to t1 f2t fn transpose t dt plus so on. Plus the last term will be alpha n integral of t naught to t1 fnt fn transpose t dt equal to 0. This will be equation number n, n set equation. Yes, are you following me? I need at least one response.
Yes, sir.
Is that okay? So now these n equations can be written in matrix form. You can see that I am following exactly the same procedure that I followed for evaluating the set of vectors for dependence and dependence. The same procedure, similar procedure we are actually developing for evaluating a set of vector functions for dependence and dependence. So these n equations I will write in matrix form. So writing these n equations in matrix form, n equations in matrix form, we have, say like this. So integral of t naught to t1 f1t f1 transpose t dt. Is that okay? Then integral of t naught to t1 f2t f1 transpose t dt. Then so on. Integral of t naught to t1. We have got fnt f1 transpose t dt. Second वाला रो क्या आएगा? Second वाला रो will be integral of t naught to t1 f2t, no sorry, f1t f2 transpose t dt. Integral of t naught to t1 f2t f2 transpose t dt, then so on. Integral of t naught to t1 fnt f2 transpose t dt. It will have n rows. It will like this. But there will be elements on all sides. The last row will be integral of t naught to t f1t fn transpose t dt. Integral of t naught to t1 f2t fn transpose t dt. So on. Integral of t naught to t1 fnt fn transpose t dt, and then you'll have here alpha 1, alpha 2, so on up to alpha n is equal to what? Is equal to 0. Is that okay?
Yes, sir.
Okay.
Yes, sir.
Now tell me this matrix जो है इसका size क्या है?
N cross N.
It's n cross n, isn't it? It's n cross n. ये तो है ही n cross 1, आपको तो पता है. So this is also n cross 1. Now this matrix, this n cross n matrix, when you evaluate it over the integral t naught to t1 all the elements, you'll get it as a constant matrix. And this matrix is basically represented as this set of equations I can write in compact form as, I write it like this, see. I name this matrix as W. And actually, it has been evaluated over the interval T0 to T1. This is what this means. Evaluated over the interval T0 to T1. Then this vector is alpha. That's equal to 0. So I have written this equation in compact form. This matrix, this is an n cross n matrix. This is this matrix actually. And alpha is this vector. And this big 0 is this 0 vector. Are you getting me? Now, this is equivalent to the system of equations that we had got last time. Last time, if you remember, I had got the set of equations like G alpha is equal to 0. This is the same set of equations, similar set of equations. Now, the same logic will apply here also. If this matrix, which is an n cross n matrix, if it is a full rank matrix, then the only solution to this system of equations, it will be a unique solution in that case, and that will be alpha equal to 0. Isn't it? Implying that for the given set of, because when alpha is equal to 0, that means the given set of vectors is linearly independent. So this implies that for the given set of vectors to be linearly independent, this matrix actually should be a full rank matrix. Because in that case only you will have a non-zero solution to alpha. Sorry, you will have alpha equal to 0. In case this W matrix is a rank deficient matrix, this alpha will have many solutions and non-zero solutions, implying the linear dependence of the given set of vectors. Do you get me? Is that okay?
Yes, sir.
This W T0 T1, this is a matrix, this is an n cross n matrix, is known as Gramian of the given vector function. This system of equations, if I call this system of equations as B, the solution of this system of equations given by B will depend upon the rank of matrix W T0 T1. That is the rank of Gramian matrix. It will depend upon the rank of Gramian matrix. If W T0 T1 is a full rank matrix, then the system of equations given by B will have a unique solution for alpha, that is this vector alpha equal to 0, which implies alpha 1 equal to alpha 2 equal to so on equal to alpha n equal to 0, implying linear independence of the given set of vector functions, implying the linear independence of the given set of vector functions. Okay. However, if W0 T0 T1 is a rank deficient matrix, the given the system of equations defined by B will have non-zero solutions for alpha implying linear dependence of the given set of vector functions. Is that clear? Is that clear to you?
Yes, sir.
Okay. So if you have a set of vector functions, now what do we conclude from here? If you have a set of vector functions and you have to check whether these vector functions are dependent or independent over some interval t0 to t1, you have to actually frame the Gramian matrix as I have defined it. You have to frame the Gramian matrix and check its rank. If it is a full rank matrix, then you can say that the given set of vector functions are linearly independent over the defined time interval. And if the given set of, if your Gramian matrix is a rank deficient matrix, you can conclude that the given set of vector functions has got some dependency over some time interval t0 to t. Is that clear? So this is what is Gramian. So that means if you have some वेक्टर हमारी वेक्टर फंक्शन जो हमने वेक्टर फंक्शन मैट्रिक्स डिफाइन की थी वो ft थी, है ना? ft we had defined like this: f1t, f2t, so on, fnt. Isn't it? This was defined in the very beginning, this vector function matrix. और हमें यही वेक्टर्स देखने हैं जो इस वेक्टर फंक्शन मैट्रिक्स के जो रोज हैं, हमें देखना है कि ये रोज आपस में डिपेंडेंट है या इंडिपेंडेंट है. So what's the procedure for that? What do you do actually? You make a Gramian matrix. And how do you define the Gramian matrix? So for checking the dependence independence, independence of rows of ft. So we define something known as Gramian of these vector functions, or Gramian of this vector function matrix. W defined over t0 to t1. We define this as, so if I write it in compact form, I can write it like this: W t0 t1, that's integral of t0 to t1 ft f transpose t dt. Because ft is this, what will be f transpose t? F transpose t will be like this: f1 transpose t, f2 transpose t, so on, fn transpose t. And their product, so you'll have something like this. So if I take this ft into f transpose t, ft into f transpose t, what will I have? I'll have ft is defined as a like this. So this is f1t, f2t, so on up to fnt. This I have to multiply by f1 transpose t, f2 transpose t, so on, fn transpose t. So if I take their product, what will I get? I'll get f1t, f1 transpose t, then f1t, F2 transpose T, so on. F1T, Fn transpose T. Then next time F2T, F1 transpose T, F2T, F2 transpose T, F2, ये transpose नहीं है यहाँ, F2T, Fn transpose T, and so on. Finally, I have Fnt, F1 transpose T. नहीं, क्या किया मैंने? Have I done it correctly? So you basically have got a set of vector functions f1t up to. So what is the size of this? What is the size of this one? This has got n rows and one column. सही है ना? Are you following me?
Yes, sir.
Yes, sir.
And this also has got 1 cross. This is 1 cross n. So the product will be n cross n. And that is, and if you integrate it, integrate over the interval, T0 to T1, we have W T0 to T1 defined as integral of T0 to T1 Ft F transpose T dt. That means each individual entry of this integrated over the time interval T0 to T1, which is known as the Gramian of vector function matrix. Gramian of vector function matrix F. जब आपको कोई भी वेक्टर फंक्शन मैट्रिक्स ft दी हुई हो और आपको इसके रोज की डिपेंडेंस इंडिपेंडेंस देखनी हो तो आप उसका ग्रामियन मैट्रिक्स डिफाइन करो ऐसे और इसकी रैंक देखो. Once you check its rank, then you can say whether the rank of this matrix will tell you about the dependence independent of the rows of this vector function matrix. So the same logic we are going to define, will be using to define the controllability Gramian. Controllability Gramian को define करने के लिए हम same logic use करेंगे. I'll take you back to the controllability tests. So what are the controllability tests that we were discussing? What was the theorem that I had stated? कौन सी theorem state की थी मैंने? Do you have the notes in front of you?
So the necessary and sufficient condition for the system defined by equation x0 is equal to ax plus b to be controllable is given by any following
जो कंडीशंस मैंने स्टेट की थी तो पहली कंडीशन उसमें ये थी कि कंट्रोलेबिलिटी ग्रामियन इज नॉन सिंगुलर और दूसरा कंडीशन ये स्टेट किया था कि कंट्रोलेबिलिटी मैट्रिक्स जो हमने डिफाइन किया था b a b a square b up to e to the power n minus 1 b is a full rank matrix, isn't it? तो वो जो ग्रामियन टर्म मैंने यूज की उस ग्रामियन टर्म को डिफाइन करने के लिए मुझे इतना आपको बैकग्राउंड मैथमेटिक्स दिखानी पड़ेगी. ये ग्रामियन आया कहां से है बेसिकली. और कंट्रोलेबिलिटी ग्रामियन को अब हम लिंक करेंगे इसी के साथ. We'll try to link the controllability Gramian with this. I will restate the theorem and then we'll go for the controllability test. Is it clear up till now?
Yes, sir.
Okay. So now I will take you back to the with this definition of this, let me first of all take you back to that controllability test theorem that we were defining. एक टेस्ट तो हमने आपको बताया, मैंने आपको दिखाया था कि डायगोनलाइजेशन से कैसे देखते हैं कि सिस्टम कंट्रोलेबल है कि नहीं है, वो तो एक मेथड मैंने आपको दिखाया था। और दूसरा टेस्ट हम प्रिस्क्राइब कर रहे थे, तो उसके लिए मैंने थ्योरम स्टेट की। बेसिकली आपका जो सिस्टम है दैट इज x डॉट इक्वल टू ax प्लस bu। x0 जो है that is defined as x0. Initial conditions are given. So the necessary and sufficient condition for the state space model given by 1, let me call this as equation 1, to be controllable is given by any one of the following conditions. First is the controllability Gramian defined as WC defined over interval 0 to t1 is equal to integral of 0 to t1 e to the power minus ATB B transpose e to the power minus A transpose T dt is non-singular. Controllability Gramian defined by this is non-singular. Isn't it? ये पहली condition थी, and second was the controllability matrix defined as UC is equal to B AB A square B so on after A to the power n minus 1B is a full rank matrix or is non-singular, one and the same thing. तो ये दो कंडीशंस हमने स्टेट की हैं जो कि आपस में इंटररिलेटेड है। मींस एक कंडीशन सेटिस्फाई होगी तो दूसरी कंडीशन ऑटोमेटिकली सेटिस्फाई हो जाती है। So the theorem says that if you have the controllability Gramian which is defined like this, तो भी हम पहले देखेंगे कि ये कहां से आया है, ये controllability Gramian को हम ऐसे कैसे डिफाइन कर रहे हैं। The controllability Gramian defined like this is non-singular and the controllability matrix which has been defined as UC is equal to this matrix. B is actually B matrix that we have in the state space model. B A B A square B up to A to the power n minus 1B is the full rank matrix. That's what we have to prove. We'll prove it, but before proving it, let's first of all try to see what this controllability Gramian is. पहले हम देखते हैं controllability Gramian है क्या। You basically आया कहां से controllability Gramian and how do we define this? You know that for the given set of state equations, what's the solution? The solution to the state space equations given by 1 has been obtained as what's the solution? Xt is equal to e to the power at x naught, isn't it? integral of 0 to t e to the power a t minus tau b u tau d tau. ये तो अब याद होना चाहिए सबको, एग्जाम भी दे दिया आपने, isn't it?
Yes, sir.
Okay. तो कंट्रोलेबिलिटी की जो हमने दूसरी डेफिनेशन ली थी, जब मैं कंट्रोलेबिलिटी स्टेट कर रहा था, जब मैं डिफाइन कर रहा था कंट्रोलेबिलिटी को, आई टोल्ड यू that for mathematical convenience we take the final state to be the origin, isn't it? So
Yes, sir.
let the final time be t equal to t1. So if I substitute it here, I'll have this x, I will write like this. X of t1 is equal to e to the power a t1 x naught. x naught को हम ऐसे रिप्रेजेंट करते हैं x0 प्लस इंटीग्रल ऑफ 0 to t1 e to the power a t1 minus tau b u tau d tau. t1 मैंने कोई फाइनल टाइम लिया जब तक मैं सिस्टम को सिमुलेट कर रहा हूँ या जब तक मैं सिस्टम का रिस्पॉन्स देख रहा हूँ, जब तक मैं इनपुट अप्लाई कर रहा हूँ सिस्टम को. So for mathematical convenience this xt1 is taken as the origin. We have already discussed that. For mathematical convenience, excuse me, I have a call. I'll just come back. Hello. Hello. Yes. What is that? Anand. I'm sorry, I had to attend some call. So for mathematical convenience, xt1 is taken as the origin. That is, xt1 we take equal to 0 vector. This is a vector. So in this equation, what do I have? So instead of xt1, I can put 0 is equal to e to the power a t1 x naught plus integral of 0 to t1 e to the power a t1 minus tau b u tau beta. Or I can write, so I can take this on this side. So this is minus e to the power a t1 x naught plus this e to the power a t1 I can take outside the integral, because the difference is, this integration is with respect to tau. So it is e to the power a t1 integral of 0 to t1 e to the power minus a tau b u tau beta. Are you following me, everybody? This is actually equal to here. Is that okay?
Yes, sir.
So we pre-multiply on both sides by e to the power minus 81. So what do we get? So e to the power minus 81, e to the power 81. You know, e to the power minus 81 is actually the inverse of this. So that will make it I. So you have minus x naught is equal to integral of 0 to t1. This will also go e to the power minus 8 tau b u tau and beta. Is that okay? Or I can write it as minus x naught is equal to integral of 0 to t1 e to the power minus. Now I can change this tau by t, change a variable. So I can write it just e to the power minus 80 b u t dt. Is that okay? So any u If U exists for any x naught, then the system is controllable. That's how we have defined controllability, is it? If you take x naught, that is the initial state anywhere in the state space, and the solution ut exists for this system of equations, then you say that the system is controllable. Are you following me?
Yes, sir.
Okay. तो x नॉट आप कहीं भी किसी भी जगह रैंडम स्टेट ले सकते हो, कहीं भी जगह स्टेट स्पेस में, और जब आप इस इक्वेशन को सेट ऑफ इक्वेशन को सॉल्व करोगे, a और b तो पता है हमको, and if the solution ut exists for this set of equations, that actually implies that the given system is controllable. Now, for that ut to exist, that will actually depend upon this. Now, what is this? What is the size? What is this matrix e to the power minus 80? This is actually a matrix, you know it. This is a matrix exponential. इसका size क्या है?
N cross N, sir.
It's n cross n. And what's the size of this?
N cross 1.
N cross 1. In general, it's n cross 1. For single input, single output systems, it's n cross 1. But in general, for multi input, multi output systems, it will be n cross p. Isn't it? Where p is the number of inputs. और उस केस में आपका ut भी जो होगा वो p cross 1 होगा. p is the number of inputs actually. Where normally because we are considering only single input, single output system, so p is normally taken equal to 1. Are you getting me? So basically आपका ये जो e to the power minus 80b है, इसका साइज n क्रॉस n है, इसका साइज n क्रॉस p है. तो ये जो मैट्रिक्स बनेगा ये वाला, दिस विल बी n क्रॉस p मैट्रिक्स. Isn't it? That is n rows and p columns. N is the number of states, p is the number of inputs. Normally जो systems होते हैं उसमें states ज्यादा होंगे या inputs ज्यादा होंगे?
State, sir.
States ज्यादा होंगे. Means इसमें number of rows ज्यादा होंगे. Number of rows ज्यादा होंगे और columns कम होंगे. So it will actually be a matrix, n cross p matrix, and the solution to this system of equations will actually depend upon the row rank of this system of this is actually ये वाला जो बना e to the power minus 80b, it is n cross p matrix. So that means it will have n rows, p columns. N rows, and each row having and the total of means each row जो इसकी entry है, हर एक row की जो entry है, p entries है हर एक row में. So this is first row, let's say, this is second row, this is third, fourth, fifth, so on up to, and every row has got how many entries? P entries. So this is 1, 2 up to p. And since this e to the power minus 80 is a function of time, so it's basically a vector function matrix. Are you getting me? Is that okay? तो ये जो given set of equations है ये वाली, इसका solution ut का unique आएगा कि नहीं, या solution ut exist करेगा x naught के लिए कि नहीं, that will depend upon this set of ये जो vector function matrix है, इसकी matrix properties पे depend करेगा, इसकी rank पे depend करेगा. तो इसमें आप देख रहे हो basically ये n cross p matrix है. N is greater than p. Normally, usually n is greater than p. Because the number of states will be greater than the number of inputs. Normally हमारा single input, single output system होता है, तो उस केस में तो आपका p1 ही होता है basically. So if you have a non-square matrix and you want to check its rank, what can be its maximum rank equal to? आपके पास अगर एक non-square matrix है, मान लीजिए 5 क्रॉस 2 मैट्रिक्स है एक, और आप उसकी रैंक देखना चाहते हो, क्योंकि नॉन स्क्वायर मैट्रिक्स है, तो ये फुल रैंक तो हो ही नहीं सकता, फुल रैंक इसमें डिफाइंड ही नहीं है, बिकॉज रैंक जो फुल रैंक है वो डिफाइंड होती है, स्क्वायर मैट्रिसेस कैन बी फुल रैंक. So if you have a non-square matrix where having size n cross p, so what can be its maximum rank equal to?
So smaller dimension.
Smaller dimension. That means at the most it can be equal to p, isn't it? At the most it can be, जैसे इस केस में it can be at the most equal to p. So that means p इसमें क्या है? p इसमें columns हैं, isn't it? ये actually n rows और p columns है ना? N rows and p columns. So in order to see whether a solution exists for this set of equations, we will have to check the rank of this matrix. E to the power minus 80b की rank देखनी पड़ेगी हमें. और इसकी rank कैसे? क्योंकि ये नॉन स्क्वायर है और ये फंक्शन ये वेक्टर ये मैट्रिक्स है ऑफ वेक्टर फंक्शंस. तो वेक्टर फंक्शन जो मैट्रिसेस होती हैं और वेक्टर फंक्शंस की उनकी रैंक कैसे देखते हैं? कैसे हमने देखा अभी? हाउ डू वी चेक द रैंक ऑफ दिस? इफ आई कॉल दिस एज ft, this is a set of vector functions. How do I check the rank of this? How do I check whether this set of vector functions is dependent or independent?
Gramian.
I define a Gramian. And how do I define the Gramian? How have I defined the Gramian for a vector function matrix ft?
Multiply the transpose.
We have defined it as, or the time interval 0 to t1, that is integral of 0 to t1 ft f transpose 3 dt, isn't it?
Yes, sir.
And what is ft? Ft is e to the power minus atb. What will be f transpose?
E cross A transpose.
Yes. So e to the power minus atb. So the controllability of the system will depend upon the linear dependence of the independence of the vector function of the rows of a vector function matrix defined as ft equal to e to the power minus atb. And we have seen that the linear dependence of the independence of a vector function matrix over some time interval T0 to T1 is evaluated by obtaining the rank of the corresponding Gramian matrix. So in this case, the Gramian will be defined as this case, the Gramian will be defined as WC 0 to T1. ग्रामीण कैसे डिफाइन करते हैं हम? W0 to T1 कैसे, या T0 to T1 कैसे डिफाइन करेंगे नॉर्मली हम? We define that as integral of T0 to T1 ft f transpose T dt. तो यहाँ पे जो आपका ft है, so यहाँ पे इंटरवल डिफाइंड है 0 to T1. ft जो आपका है that is e to the power minus atb, then f transpose T. Already f transpose T. So your Gramian is defined as W T0 to T1 is defined as integral of T0 to T1 ft f transpose T dt. So ft तो ये है, इसका ट्रांसपोज that is e to the power minus at इसका ट्रांसपोज dt. That is equal to WC we have defined, sorry. So this is WC 0 to T1 equal to integral of 0 to T1 e to the power minus atb. Transpose इसका product of matrices का, so this will be B transpose e to the power minus A transpose T, which is actually how we have defined the controllability. Is that okay? Now, do you understand where from this controllability Gramian has come? अच्छा, तो जो हम थ्योरम स्टेट कर रहे थे, थ्योरम में हमने स्टेटमेंट क्या दिया था कि अगर आपका सिस्टम आपका कंट्रोलेबल तभी है कि नेसेसरी और सफिशिएंट कंडीशन उसके लिए ये है कि आपका जो कंट्रोलेबिलिटी ग्रामियन हो वो नॉन सिंगुलर हो, isn't it? The controllability Gramian must be non singular. तो कंट्रोलेबिलिटी ग्रामियन के नॉन सिंगुलर होने के लिए जरूरी है कि ये वाला जो फंक्शन है, इसकी जो रोज हैं वो लीनियरली इंडिपेंडेंट हों, isn't it? हमने थ्योरम स्टेट की कि किसी भी सिस्टम की कंट्रोलेबिलिटी के लिए नेसेसरी और सफिशिएंट कंडीशन ये है कि जो कंट्रोलेबिलिटी ग्रामियन डिफाइंड लाइक दिस, इट मस्ट बी नॉन सिंगुलर. So what does that in turn imply? For this to be non singular, how can this be non singular? This can be non singular only if this function ft has got all the rows linearly independent. Are you getting me? Is that okay? कंट्रोल किसी भी ग्रामियन मैट्रिक्स,
Yes, sir.
किसी भी ग्रामियन मैट्रिक्स की डिपेंडेंस इंडिपेंडेंस के लिए जरूरी है कि आपका जो ft है या f ट्रांसपोज t जो भी हो, उसका जो रोज या कॉलम रैंक जो है वो उसकी जो डिपेंडेंस है वो इंडिपेंडेंट होनी चाहिए. तो उसी को यूज करके हम इस थ्योरम को प्रूव करेंगे. नाउ आई विल गो टू द प्रूफ ऑफ द थ्योरम. इज दैट ओके नाउ? इज दैट ओके सो फार?
Yes, sir.
Now we will go for the proof of the theorem, because now we already know what is the controllability Gramian. So first we will take the, because we have to prove the necessary and sufficient condition. Well, first we will prove the sufficiency. Sufficiency will be if the controllability Gramian is non-singular, the system is controllable. This is what we will prove. Okay. So if we are assuming that WC0 T1 is non-singular and we have to prove that the system is controllable. तो अगर WC0 T1 non-singular है तो इसका इनवर्स एग्जिस्ट करेगा, isn't it?
Yes, sir.
If WC0T1 is non-singular, that implies WC inverse 0T1 exists. तो जो हमारा कंडीशन था कंट्रोलेबिलिटी का, जो हमने अभी कंडीशन फॉर controllability is minus x naught equal to integral of 0 to t1 e to the power minus atb ut dt. So if the solution exists for any, if you have ut such that this equation is satisfied, then you say that the system is controllable. Now since WC inverse 0 t1 exists, I assume, or since WC inverse 0 t1 exists, ut equal to B transpose e to the power minus A transpose T, WC inverse WC inverse zero T1 X naught can be applied to the system. Can be applied as an input to the system. Because you know WC inverse exists, so I can evaluate it, and I can put ut equal to B transpose e to the power minus A transpose T WC inverse 0 T1 into X naught, and I evaluate the right hand side of this equation. So what do I get here? This is, or I'll put it equal to minus this thing. So I can evaluate it as integral of 0 to T1 e to the power minus AT B ut dt equal to integral of 0 to T e to the power minus AT B ut I have put equal to minus B transpose e to the power minus A transpose T WC inverse 0 T1 X naught dt, which is actually equal to minus I can take out. This is 0 to T e to the power minus AT B B transpose e to the power minus A, sorry, yes, E transpose T, then dt, then WC inverse 0 T1, then X naught. Now, dt I will take inside. What is this equal to? This is your WC 0 to T1. So this will be equal to minus integral of 0 to T, T1 actually this is. This is WC 0 T1. Then this is WC inverse 0 T1 into X naught. Sorry, this integral will be inverse. Because this with integral, this is equal to WC. So now this, since this is this we have assumed that this is non-singular, so this is this is invertible, so this will be equal to I, which is equal to minus X naught, which is actually the condition for controllability, which implies condition for controllability is satisfied, implying that the system is controllable. That means if the controllability Gramian is non-singular, then the system is controllable. The proof is a bit hard. If you have any problem, I can repeat it. जब तक बोलोगे नहीं मैं समझूंगा नहीं. Yes.
सर वो u of t का वैल्यू कहाँ से आया सर? u of t इज इक्वल टू माइनस बी
UT बेसिकली देखो, बेसिकली मैं ये प्रूव करना चाहता हूं कि अगर कंट्रोलेबिलिटी ग्रामियन नॉन सिंगुलर हो तो उस केस में आपका सिस्टम कंट्रोलेबल होता है. तो कंट्रोलेबिलिटी के लिए हमने देखा है कि ये वाली इक्वेशन के लिए हर एक एक्स नॉट के लिए यूटी एग्जिस्ट करना चाहिए. दैट इज बेसिकली व्हाट इज कंट्रोलेबिलिटी. if ut exists for any random x naught and any random x naught can be taken to the origin through ut, then we say that the system is controllable. Now what we are saying, because see this equation on the whole is very hard to solve क्योंकि इसमें जो इंटीग्रल वाली टर्म ut है ये इंटीग्रल में ही आती है. So basically without actually solving the system of equations we are trying to see whether the solution exists or not, and we are trying to correlate it to the rank of some matrix which we have called as the controllability Gramian. तो हमने देखा कि हमने एक थ्योरम स्टेट की कि अगर कंट्रोलेबिलिटी ग्रामियन जो हमने डिफाइन किया है WC0T1 and we have defined it in a particular form and you already know the mathematical background for that, if that is non-singular we say that the system is controllable. So now we in order to prove the sufficient condition or sufficiency of this theorem, we first of all assume that this WC0T1 is in fact non-singular. Non-singular means that its inverse will exist. तो इनवर्स का एग्जिस्ट होना मीन WC इनवर्स को मैं इवैल्यूएट कर सकता हूं क्योंकि ये एग्जिस्ट कर रहा है. WC तो खाली डिपेंड कर रहा है B और A पे और वो तो हमें ऑलरेडी पता है वो क्या है. So what we are doing that I am, because mathematically how I am proving it, I am putting ut is equal to minus B transpose e to the power minus A transpose T WC inverse 0 T1 into x naught. ये मैंने इस फॉर्म में क्यों रखा क्योंकि मुझे फाइनली प्रूव करना है कि इसको मैं अगर इवैल्यूएट करूं it will come out to be equal to x naught. So any x naught if I substitute here, anywhere any random x naught if I substitute here, I will, when I solve this equation, this right hand side of this equation, I'll end up with minus x naught, which is actually the required condition for controllability. So this input can be applied to the system. I have substituted ut for this. तो ut यहाँ पे substitute करके हमने थोड़ी बहुत मैथमेटिकल जगलरी की mathematical manipulations करके we have seen that this finally reduces to this expression wherein this e to the power minus at b transpose e to the power minus a transpose t dt has already been defined as the controllability grammar with the integral, and this with WC inverse 0 T1 तो input term से आ गया और ये दोनों में क्योंकि WC 0 T1 full rank matrix है, so the product of two full rank matrices, product of the matrix and its inverse, it's equal to I. So this will come out to be equal to minus x naught, which is actually the left hand side of this equation, therefore satisfying the condition for controllability. It's a mathematical proof and you have to do it like this. Are you getting me?
Yes, sir.
So sufficiency is theorem की prove हो गई. Sufficiency means that if the controllability Gramian is non-singular, the system is controllable. Now we will prove the sufficient condition. Sorry, necessary condition. Necessary condition means we are assuming that the system is controllable and we have to prove that the controllability Gramian is non-singular. For a controllable system, the controllability Gramian is always non-singular. So that will be the necessary condition. So we'll now prove the necessary condition for this theorem. We'll prove this by contradiction. We'll assume that the system is controllable, but controllability Gramian is singular. Controllability Gramian हमने कैसे define किया? WC0T1. It's singular for some time T1. The necessary condition will prove a contradiction. Controllability gram in singular hona means controllability gram in, you know, it's defined as integral of 0 to t1 e to the power minus atb b transpose e to the power minus a transpose t dt. मीन्स इसके जो रोज हैं वो लीनियरली डिपेंडेंट है. कंट्रोलेबिलिटी ग्राम मीन बीइंग सिंगुलर means that or implies that the rows of e to the power minus atb are linearly dependent. Linearly dependent means जो इसके रोज हैं अगर उन रोज की मैं लीनियर कॉम्बिनेशन लूं through some alphas, there will exist a non-zero solution to that alpha. Are you getting me? Please try to follow me properly. So controllability Grammar being singular, because we have assumed that controllability Grammar is singular, but the system is controllable. So controllability Grammar being singular implies that the rows of e to the power minus atb are linearly dependent. Are linearly dependent. So what does that imply? What does that imply? That implies that there exists. It implies that there exists a non-zero n cross 1 vector alpha such that alpha transpose e to the power minus atp equal to 0. ये जो फंक्शन ft है, f है ना बेसिकली ये, दिस इज बेसिकली ft. इसके जो सभी एंट्रीज हैं उनको मैंने ये एक्चुअली ऐसे है, alpha is like this. So this is alpha transpose is alpha 1, alpha 2, so on up to alpha n. और ये इसके रोज हो गए f1t, f2t, so on up to fnt. I put it equal to 0. So this will be alpha 1 f1 plus alpha 2 f2 plus so on alpha n fn equal to 0. I take the linear combination of the rows of this vector function matrix and try to, and because I have assumed that this is singular, that means there exists a non-zero solution alpha to this. Is that okay? Is that okay?
Yes, sir.
So there exists a non-zero solution to this. So alpha transpose e to the power minus atb equal to 0. Now from the definition of controllability, you have minus x naught equal to integral of 0 to t1 e to the power minus atb ut and dt. So if I multiply on both sides by alpha transpose, what will I get? This will be minus alpha transpose x naught is equal to integral of 0 to t1 minus alpha transpose e to the power, sorry, this is not minus, alpha transpose e to the power minus atb ut dt. Now what is this alpha transpose e to the power minus atb equal to? Alpha transpose e to the power minus atb. What's this equal to? This is equal to 0. So the right hand side of this becomes equal to 0. So I get alpha transpose x naught equal to 0. Could you follow the steps?
Yes.
So I get alpha transpose x naught equal to 0. Now, since the system is controllable, so any x naught is possible. So what do? I put x naught equal to alpha. Alpha is a vector, n cross 1 vector. So controllability implies that if you start with any random vector, you should be able to get ut. So I start with a vector alpha, let us say. What will I get? I get alpha transpose alpha equal to 0. Isn't it? So alpha transpose alpha equal to 0 can be true only under one condition. What's that condition? Alpha transpose alpha is basically the dot product of vector alpha with itself. So this can be true only if alpha is equal to implying our assumption that the controllability, this actually contradicts our assumption. Controllability Gramian, our assumption that the controllability Gramian is singular is contradicted. Because we are saying alpha equal to 0. So we have contradicted our own assumption, which actually implies that the controllability Gramian is non-singular. Do you get me? Rule number 1. Enrollment number 1 is in the class.
Yes, sir.
Tell me.
जी सर.
Tell me, समझ आया कि नहीं?
सर completely समझ नहीं आया. मैं पढ़ूंगा सर, फिर बता सकता हूँ सर.
You have to go through it once.
Yes sir. तभी आएगा
एक बार
समझ.
देख के पूरे steps देख के आपको कहीं पे भी कोई problem हो, you can just tell me in the next class.
Yes sir.
Rule number 2. Rule number 2. 3. Rule number 3. The CR is absent today also. Rule number 3. Four. Five. I had told you initially also that you should always log in with your enrollments. Some people have logged in with their names. तुम लोगों को कौन सी भाषा समझ में आती है? Rule number 6. 7.
Yes, sir.
Yes, tell me, could you understand this proof?
Yes, sir. समझ में आया, but एक बार फिर से पढ़ना पड़ेगा.
आपने पढ़ना तो जरूरी है एक बार. इससे पढ़ना है. You have to go through it once and then get back to me in case you face any problem anywhere.
Okay, sir.
Rule number 8.
Yes, sir.
Okay, 9.
यस सर.
आदर्श कुमार, हाँ जी बताओ आप मुझे.
जी सर, आगे सर एक बार दोबारा देखना पड़ेगा पर.
Rule number 10. Sanna Shokar.
Yes, sir.
Okay, rule number 11. 12. 13. So for the major exams, we are going to strictly follow the attendance rule. We will not allow anybody who has less than 75% of attendance. Mind it. Roll number 15.
यस सर
वासिद अली, हाँ जी।
सर यस सर आ गया सर
Are you
आया
following?
आया सर समझ में बाकी अभी कुछ अभी पढ़ना पड़ेगा सर तो फिर जो प्रॉब्लम आएगी
पढ़ना पड़ेगा, बड़ी मजबूरी है पढ़ने की तुम लोगों को। 16, roll number 16.
Yes, sir, present.
17, 18, 19,
Yes, sir.
20, 'Amir Ali, what's your roll number? Amir Ali, are you online? Anurag Jaiswal, पीयूष ठाकुर,
यस सर
आप लोग, आपको कहा था ना कि आप एनरोलमेंट से ये लॉग नाम चेंज करना, यू शुड हैव योर एनरोलमेंट नंबर शुड बी इन योर नेम।
यस सर कॉलेज की आईडी से आया था इसलिए इसमें नाम नहीं है सर नेक्स्ट टाइम आई विल कम विद माय आईडी
खालिद मकबूल,
अस्सलाम वालेकुम सर।
वालेकुम सलाम, व्हाट इज योर स्टेटस? आप भी अगली बार ना अपने एनरोलमेंट नंबर से ये
सर ये नए आईडी से ज्वाइन किया, वही प्रॉब्लम थी, इसमें नाम नहीं चेंज करना।
इरशाद तांत्रे,
Yes, sir.
इनायत अशरफ, Inayat Ashraf just logged in and they are somewhere. They are not online. Danish Ahmed, Asma Tayyub.
Yes, sir.
So, are you following the lectures?
Yes, sir.
What's your performance in the examination? Have you performed well in the exam? Yes, Asma.
Yes, sir.
कैसी परफॉर्मेंस रही एग्जाम में आपकी?
सर ठीक थी।
अनुराग जायसवाल.
Yes, sir.
What about you? I called your name before this also.
No, sir. You called me right now. Sorry, sir. I was not able to hear.
Huh?
I was not able to hear you, sir. Sorry, sir.
Why were you not able to hear? आप कैसे सुन रहे हो?
Sir, that time I was not online, sir.
You were not what?
I was not listening to your lecture, sir. Sorry, sir.
Why?
Sir, sorry, sir. Personally, I've left the classroom, sir. Sorry.
तो लॉगिन क्यों करके रखा हुआ है बेकार में जब लेक्चर ही अटेंड कर रहे थे?
No, sir. For some time, sir. For 15 minutes, I was not online.
Why like that? Why was it like that?
Hello.
I am noting your enrollments. I am noting your names. Amir Ali.
Yes, sir.
What about you? You also didn't respond to my call.
Sir, I was not online.
You were not online. Why?
सर थोड़ा काम था इसलिए।
अच्छा, क्लास के टाइम में आपको क्या काम था?
सर वो घर पे बुला रहे थे।
I'll just throw you out of the class. I don't like students. I don't tolerate students like you. Some people have already started leaving the meeting because the names I have called, they have started leaving the meeting. Piyush Thakur will be absent for today. Sriram. Roll number 82. Sriram.
Yes, sir. Yes, sir.
Anji, are you following the lecture?
Yes, sir.
What about today's lecture?
Yes, sir. समझ आया सर मैं बट अभी वापस पढ़ूंगा सर नोट से।
Okay. Atul Saroj.
Yes, sir.
What about you?
Yes, sir. अभी बस इसको रिपीट करना पड़ेगा, बाकी आ गया समझ में। हेलो,
Roll number 53, Abdul Hanan.
Yes, sir.
Yes, Hanan, tell me. What about you?
Sir, idea आ गया sir.
Idea आ गया, just follow it. I'll be asking questions tomorrow regarding this.
Okay, sir.
Saryan Gupta.
yes sir.
Saryan
Yes,
Gupta.
Yes, sir. आ गया।
Saryan Gupta, you are almost 52. आपका तो म्यूट ही आ रहा है यहाँ पे. Who is talking on behalf of Saryan Gupta?
सर मैं ही हूँ सारंग गुप्ता सर।
आपको पता है लास्ट टाइम आपको प्रॉब्लम कितनी थी अटेंडेंस की?
Sir.
So if I find you missing from a single class, I'll just fail you in this course.
Sir, I'm
Yes, sir. 20 जी सर आया समझ.
Just go through the lecture properly and see wherever you face some problem, just contact me. Just try to ask me in the next class.
Okay, sir.
Wherever
Okay.
you have, in the next class. I'll stop this time. I'll
जी
give
sir.
some time, half an hour time because अभी time है कुछ class में. Just go through it once, and tomorrow because we have a class tomorrow also from 10 to 11. Just tell me regarding this. Sarian Gupta has already left the class. I'll not tolerate these idiots in the class. So we'll be stopping here. And the next portion of the theorem, that's the second part of the theorem, we'll be discussing in the next class tomorrow. So just use this time to just go through what has been taught today and try to see where, if you have any problems somewhere, just discuss with me tomorrow. Thank you all. Thanks. You can leave the meeting.